Screen. Okay, so we are here discussing the topic of congestion control, which boils down to the problem of bandwidth allocation, and hence we discussed an algorithm of fair and efficient bandwidth allocation, namely the AIMD algorithm, additive increase, multiplicative decrease. And we moved on to discuss the congestion control, the summary and the technique offered by TCP. We know that TCP is a closed loop, feedback driven, host based, window based congestion control protocol, and it tries to obtain feedback from the network, and then obviously runs the AI and MD part based on these formulas. Okay, and this is the behavior of one host when it is plotted. Its window size is plotted against the time, which may be in RTT. And the behavior is in sawtooth form, because you have an AI part and then you have an MD part, which decrease the rate by cutting the window size in half. And then we saw that we already have been maintaining a caveat of last byte sent minus last byte act should be less than equal to receive window, and this caveat was being maintained to ensure flow control. And now we have another caveat to be maintained, which is to ensure congestion control. Again, we need to have the last byte sent minus last byte act should be less than equal to congestion window size. So the final caveat that needs to be maintained by the sender should be something like that. Okay, it should be the minimum of the two windows. Okay, C wind or R wind. And then we also observed very beautiful phenomena exhibited by TCP, the transmission control protocol, which says that TCP self-clocked itself without having a look at the network. TCP somehow self-clocked itself on the rate at which the bottleneck or the slowest link in the entire path wants it to operate. And this is possible because of the fact that the new segments are governed by the acknowledgement of previous segments being received, and since the acknowledgement will maintain a spread because of the spread that was maintained while transmitting the new segments by the router on the slowest link, then that's why the new segments will be clocked by these acknowledgements coming back to the receiver. And the same phenomenon we saw on the in the animation as well. And so the protocol, the transmission control protocol, it bring down its rate on the rate of the bottleneck link. So that's what we call self-clocking. Okay. And then we discussed, then we moved towards the next part, and we started this part. So let's continue from here onwards. Okay, and we discussed that TCP, we want to study, to discuss the algorithm of TCP congestion control, and we will discuss three different algorithms: TCP Tahoe, TCP Reno, and TCP New Reno. And these happen to be the the earliest congestion control algorithms. Before these algorithms, TCP exists, but it was without the property of congestion control. So TCP just perform reliable data transfer and maybe flow control, but not congestion control. Okay. So the first of these algorithms was TCP Tahoe. Then TCP Reno was proposed as an optimization, as an improvement on Tahoe, and then TCP New Reno as a slightly more improvement on TCP Reno. Okay. And I said that before moving to the three algorithms, to the three techniques, let's first discuss the three phases. And we discussed TCP congestion avoidance, slow start, and FRFR. So the three phases were slow start, congestion avoidance, and fast retransmit and fast recovery, FRFR. Okay. Actually, these are the two real phases, slow start and congestion avoidance, but FRFR is also an important phenomenon, so we can call it as a phase because it happens for mostly, in most cases it happens for a time period of 1 RTT. Okay, and we discussed the difference between slow start and congestion avoidance, and we saw that okay, in slow start, the window size keep doubling every RTT, and to keep doubling the window size in every RTT, we need to run this formula after every egg. Okay, so we need to run after receiving every egg, we need to increment the window size by 1. Okay, and in the case of congestion avoidance, we need to increment the window size by 1 over C wind after every egg, which will result in an increment of 1 packet after every RTT. Okay, so after every RTT, 1 packet is being added to the window size, but here after every RTT, window size is being doubled. Okay, so everything is clear up till now, Ji, to everyone. We can continue from this point onward. Okay, we have studied up until this point yesterday. Okay. Right, Ji. So yesterday we also discussed a concept that slow start helps us to achieve our ideal congestion window much quickly as compared to the actual AI phase. So I mean, if we use a mixture of exponential increase and then linear increase, it is better and it is fast as compared to only linear increase. Obviously, rightly so, it makes sense, and I gave some examples in quantitative example in yesterday's lecture. That for instance, let's say if our ideal window size is if our ideal window size is, let's say, 1500 over here. Okay, 1500 segments per RTT. Okay, and we want to achieve this ideal window size as soon as possible. The AI part will take 1500 RTTs, because it keeps increasing the rate by 1 segment every RTT. Okay, so the AI part will take 1500 RTTs to reach to this ideal window size. But on the other hand, let's say if our slow start threshold is equal to 1024, and after this value we will move to the AI phase. So you see, we will have an exponential increase up until 1024. Okay, and we will only take 10 RTTs to reach to 1024, because it will be 1, 2, 4, 8, 16, 32, 64, and up to so on 5, 12, and 1024. Okay, so we will just need 10 RTTs to reach to 1024, and after that another 500 RTTs. So I mean, the difference is huge. So this combination will take us 510 RTTs, and it's much faster as compared to this one with only the linear increase. So but the question still remains, what should be the value of the slow start threshold? Okay, what should be the value of slow start threshold? And this is the answer to this question, that obviously initially we don't know what should be the value of slow start threshold. So initially we just assume a random value. Okay, and in modern day internet, usually a value of 64 kilobyte is taken as the value of SS thresh. Okay, slow start threshold at the beginning. And please note, in TCP, window size is represented in bytes, right? So 64 kilobytes is the value of slow start threshold. So I mean, if you start from 1 MSS and one maximum segment size is about, if we take the example of Ethernet, we know the MTU is a 1500, and in that case MSS would be 1460 bytes, right? Okay, you know the relationship between MTU and MSS, right? So if we start with this window size, this is the value of C wind, we can do the exponential increase until we reach 64,000 bytes. Okay, 64 kilobytes. Okay, right? So in fact, I'm wrong. It should not be 64,000. It's something more than that. It's in terms of byte, it's 65,000, because 1 kilobyte is not 1000 bytes. It's 1024, right? So it's whatever is the value. So until that value, we will keep going until with the slow start. Okay, TCP slow start phase, and then after that we will move to the congestion avoidance phase. But this is only the initial value that we will set, but because we don't know the slow start value. But other than that, during the whole transmission, the slow start will be set with the help of this you know this this technique. Okay, and we'll do what? we will set the slow start value to half of congestion window value before timeout. Okay, so I mean after this initial value, uh, we will set the slow start value whenever a timeout occur, whenever a packet loss is detected, and we will set the value of half of the C-wind value when the timeout occur. Okay, let me just give you an example. Okay, let me just give you an example. So for instance, over here, just have a look at how SS plus AIMD is working together. Okay, slow start plus AIMD. And by the way, this is exactly, we have not studied the algorithm, but this is exactly how TCP Tahoe works. Okay, so somehow we are studying our first variant of TCP congestion control, which is TCP Tahoe. Okay, this was the first ever congestion control algorithm which was made part of TCP algorithm. Okay, TCP protocol. Right. So on the y-axis, you can see that it's congestion window size in segments. Obviously, for our ease, we will always take window size in number of segments instead of bytes. Okay, but you can intuitively imagine that actually the window size is in bytes. Okay, and that can be observed in Wireshark as well. Okay, and on the on the x-axis we have the round trip time. Okay, so number of RTTs. So first RTT, second RTT, third, and up to so on. Okay, and y-axis we have the congestion window size in number of segments. Okay, so you can simply multiply that by 1460 and you can have the number of bytes as well. So 2 times 1460 and 4 times 1460 and up to so on. Okay, so we start from congestion window is equal to 1. Okay, initially we send the we send one packet. Okay, in the first RTT, at the start of first RTT, and after the first RTT we should have received one ACK. Obviously we are only considering correct working. Okay, we are not right now considering any problem. Okay, so as the animation suggested and as the time sequence diagram in the previous slide suggested, that after one acknowledgement received, we increment the window size. Okay, after one RTT by 1, so we send 2 packets, and please note we are in the slow start phase. So in slow start phase we increment the window size by doubling the window size by in every RTT. So 1, 2, and then 4. Okay, increase exponentially only till slow start threshold. Okay, and up to so on, and then 8 and 16. And let's assume that this is the point where the slow start threshold is being hit. Okay, so let's assume that this is the point where we reach the 64 kilobyte threshold, which was the initial value that we set. Okay, and after that we move to the linear increase. Okay, to the AI part, congestion avoidance part. Okay, and we increase additively after the slow start threshold. So after from 4th to 5th RTT, we move from 16 to 17, and then 17 to 18, and 19 and 20. Let's assume then that in the 7th to 8th RTT, when we send 20 segments, one of them got lost, and we had our timer expired, and we detect this loss of segment. Okay, we detect that the segment was lost, and then obviously we need to run the MD part. And please note that the MD part of TCP Tahoe is a bit different, because remember that this was the first ever congestion control algorithm. Okay, so the world was really the world actually was trying to recover from a very bad state of internet, the congestion collapse, and the obviously the behavior was very much very careful. All right, so the approach they take in the MD part is that they bring down the congestion window to 1. They don't cut it into half, they bring down the congestion window to 1. Okay, so at timeout, this is the event is timeout, and the action which take place is you bring down the C wind to 1, and you put the SS thresh, the value of SS thresh, to congestion window divided by 2. Okay, so the value of congestion window was 20 at this time. At this time the value was 20. Okay, so you set the value of slow start threshold as C wind by 2, which is 10, which is 20 by 2, which is 10. Okay, and next time the threshold will be 10. Okay, that's what I was trying to convey in the previous slide. In the first instance, we don't know the behavior of the network. So in the first instance, we set the value of slow start threshold as some random safe value, which is 64 kilobyte. Okay, and in the next instance, after that, the timeout will govern. So whenever we have a timeout, we will set the slow start value half of the congestion window at the time of timeout. Okay, so it was 20 over here. We set it C-wind by 2 as 10. So again, we move to the slow start. So we moved to C-wind is equal to 1, and we went in the slow start phase, which is 1 and then 2 and then 4 and then 8 and then 10. But after 10, we move to linear. Okay. After 10, we move to linear. So then 11, then 12, and then 13, and up to so on. So this is a illustration of the working of slow start plus AIMD part, and this is exactly how TCP Tahoe works in algorithmic sense. This is exactly how TCP Tahoe works. Okay, I have a chat message.
Sir? Sir,
Oh no, this is something else, some other student. Okay, yes, please, question.
सर क्वेश्चन ये कि सेकंड जो मल्टीप्लिकेटिव डिक्रीज आएगा उसके अंदर फिर डिवाइड बाय 2 नहीं हुआ करेगा, फिर हमेशा 10 पे ही रुकेगा थ्रेशोल्ड, राइट?
Not हमेशा 10 नहीं होगा. It will not be always 10, but rather it will be whatever was the value of timeout. So for instance, अगर timeout यहाँ पे ना हुआ होता, okay, and we kept on going, then whatever was the value जहाँ पे हमारे पास timeout होता, उस जगह पे जो C-wind की value थी, that value divide by 2, okay. So for instance, right now the threshold was set at 10. Let's assume that we from 15 to 16 we moved. Okay, so 10, 11, 12, 13, and then 14. Let's assume right at this moment there is another timeout. What will happen? At this timeout, again C-wind will be set to 1 down over here, and the congestion and the slow start threshold will be set to C-wind by 2. The value of C-wind is 14 right now. It's 14. Okay, so 14 by 2, it will be 7. And next time when you will move from 1 to 2 and then 2 to 4 and then 4 to 7, you will move from 7 onward to linear increase. Okay, so at slow start threshold you will leave the exponential increase and you move to linear. Okay, so this is the definition. At every timeout you set the windows into half. Okay, and this is exactly TCP Tahoe, working of TCP Tahoe. Okay, now let's move to our last phase, which we had not discussed so far. I told you guys that first we will discuss the 3 phases: the slow start, congestion avoidance, and FR. Okay, fast retransmit, fast recovery, and then we will go to the algorithms. Okay, that's another thing that while studying slow start plus AIMD, we happen to study the TCP Tahoe algorithm, but that was not our mandate in this slide. I just told you guys that this is exactly TCP Tahoe, but first we wanted to discuss the 3 phases. So we have discussed slow start and congestion avoidance. Now the third thing is that FR, fast retransmit and fast recovery. Let's postpone our discussion of fast recovery. Let's just focus on fast retransmit only. Okay, right now. Now, up until now, the only technique we are using to detect loss is what? Anyone? Up until now, the only technique that we are using to detect segment loss is what?
Acknowledgement received नहीं हुई थी.
Sir, timer out and
acknowledgement timeout, sir.
No, there is nothing like acknowledgement and timeout. I mean, I know you know the concept. Just the right way of saying would be, I mean, just timer getting expired. Okay, timer expire हो जाता है, timed out हो जाता है. Okay, so और timer segment के लिए maintain हो रहा होता है, तो we can say segment a particular segment received new and timer expired. So simple, timer was the technique, right? Timeout hota hai, and then we retransmit that particular packet. Okay, up until now this was the only technique. Now we are going to introduce another technique, and that is what we call fast retransmit. Usually the timeout period is often relatively long. Okay, and we will have that long delay. Now please note that, you know, we, this is actually the not only the mantra of networking, but the mantra of the whole research in the entire world, that we always want to optimize on things. We want to keep asking, as a mankind, you know, we want to keep asking a question: can we do better? And you notice that we had those alpha and beta formulas to, you know, calculate the timeout, and now we are trying to, TCP is trying to improve further on that. So the technique that it is trying to adopt here is that, generally, yes, we want to have the timeout to be very close to the, you know, RTT plus some margin. We had already studied that topic, but I mean, still that timeout is, you know, relatively a bit long duration before we declare that that particular segment is being lost. So there is another technique, a very good one, okay, and this technique is also something which, you know, which ensures you that, you know, most likely the segment would have been lost. And what is this technique is that you detect segment loss. You are detecting with the help of timeout, yes, but you detect segment loss before the timeout via duplicate acknowledgements. Now we know that this is something that TCP do. TCP do something like that, that, you know, you send a segment with sequence 92 and it has 8 byte of data. Then you send a segment with sequence 100 and it has 20 byte of data, and then the segment after that and after that and after that, okay. But what if this segment would have been lost? Now the receiver would do what? It will, you know, buffer all these segments, but we know that, like selective repeat, it will buffer out of order segment, will not discard these segments. But like GBN, it only send cumulative acknowledgement. So if there is a gap over here, you know, the acknowledgement after receiving this segment and after receiving this segment and after receiving this segment would be ACK of 100. So duplicate acknowledgement, this is the original acknowledgement, okay. I received 92 and 8 bytes, which means 92 to 99 I received. Now I expect byte 100 from you, okay, and I did not receive byte 100, I received something else. Okay, I buffered it, but duplicate acknowledgement of 100. I received something else, I buffered it, but duplicate acknowledgement of 100. I received something else, I buffered it, but duplicate acknowledgement of 100. TCP says that instead of waiting the whole timeout period, what I will do is that if I receive 4 acknowledgement, 1 original and 3 duplicate, okay, so that is why it is called triple duplicate ACK rule, okay, uh, 3 dup 3 dup rule, okay. So if I receive 4 acknowledgements, 1 original and 3 duplicate, what I will do is that it is highly likely, because I mean, I am receiving acknowledgements, okay, it's just that I am receiving duplicate acknowledgements of something. So it is highly likely that the segment after this particular segment must have been lost, because I mean, if the network is capable of delivering data to my end, okay, right, so I am receiving every duplicate acknowledgement suggests that one more segment has been received correctly by the receiver. That's why it's sent duplicate. But I am not receiving, you know, acknowledgement with the sequence number 120, because this one has 100 to 119 bytes of data, okay. So I should receive 120, but I am receiving duplicate acknowledgement of 100, 100, 100. So I will safely assume, which is, you know, most likely, you know, 99.9% out of 100% times it is right, that at third duplicate acknowledgement I should fast retransmit instead of waiting for the timeout, okay. So that's what the rule says over here. If the sender receives 3 acknowledgement for the same data, it will resend the unacknowledgement segment with smallest sequence number, because of the fact that it is highly likely that unacked segment must have been lost. So why should I wait for the timeout, which is a slightly longer duration, okay. So this is the technique of fast retransmit, okay. And when fast retransmit happens is that, I'll go back to this later, okay. I mean, fast retransmit still suggest the loss of segments, so we will still do MD part, okay. But I mean, we are just avoiding slightly longer timeout, okay. That what we would have been doing in the case of in the case of loss detected by timer technique, okay. So now we have studied 2 techniques to detect segment loss. One technique is the timeout and the second technique is triple duplicate acknowledgement, okay. So this is the first FR, okay, fast retransmit. Now
और ये
we'll
3
see the
duplicates
second
की कोई
FR.
reason है?
It's just a safe number to assume, because the thing is, if you look at this example, I mean, it can be 4 duplicate rule or 5 duplicate rule, but I mean, if you are receiving acknowledgements after that, after the original acknowledgement you are still receiving duplicate acknowledgement, then this certainly means that, I mean, the packets later on are being received correctly, right? So that definitely suggests that this gap would have been lost, this one packet would have been lost. Okay, so I just retransmit. It's not there is no real rationale behind apart from the fact that it is empirically proven, and less than 3 is not safe, and greater than 3 is just waiting for more unnecessary duplicate acknowledgement. So I mean, just imagine intuitively, you send some segments and you are receiving acknowledgements in order, and then you start receiving duplicate acknowledgements, and you receive 1, 2 and 3 duplicate acknowledgements. It is very safe to assume that if I am receiving acknowledgements but not the one that I expected, then that definitely means that the packet in the middle must have been lost, and let me just fast retransmit that packet. Okay. So the second portion of FR, so FR, okay, so fast retransmit and fast recovery. What does the fast recovery means? It's very simple, very simple, and different TCP algorithms, different TCP flavors use different version of fast recovery. Okay, right? Interestingly, TCP Tahoe do not use fast recovery, right? So TCP Tahoe just uses slow start and congestion avoidance and fast retransmit. It does just that. Okay, while TCP Reno, it uses fast recovery in a different way, and TCP New Reno uses fast recovery in a slightly different way. Okay, but the difference is very small difference, so it should not be a problem. Okay, we'll just study that. I have quite a low attendance today. Usually the number is way up in 40s. Anyway, not that low, but just slightly low. Right. So, what is the idea of fast recovery? Okay, when fast retransmit detects the 3 duplicate acknowledgement, okay, you start the recovery process from the congestion avoidance region and use X in the pipe to pace the sending of packets. Okay, right? I'll just comment later in the on the second half of the sentence. Okay, this is exactly the technique used by New Reno, TCP New Reno. Okay, I will comment later on this technique when we will be studying TCP New Reno. Okay, and I will comment on this first half, start the recovery process from congestion avoidance region. This is the technique used by Reno. So I mean, the New Reno uses both of these things. New Reno uses the whole sentence, does both. The New Reno starts the recovery process from congestion avoidance region and use the X to pay in the pipe to pace the sending of packets. This is the TCP New Reno, and so it does both A and B. Let's call this A. Let's call this B. So New Reno does both A and B. Okay, but Reno does just A. Okay, Reno does just A. Okay, it do not use the X in the pipe to pace the sending of packet. It just starts the recovery process from congestion avoidance, and Tahoe does nothing. Okay, neither A nor B. Okay, so Tahoe do not use the fast recovery thing. Okay, it just use slow start plus congestion avoidance plus FR, fast retransmit. Let's study and then things will be clear, so don't worry about this thing. Okay, so fast recovery will happen when fast retransmit will happen, but how? We'll study in these 3 different algorithms. Okay, we'll study in these 3 different algorithms. Right, so moving on, our first flavor, our first algorithm, we have already seen it in the previous slide set, but we just did not call it Tahoe at that time, but it was actually TCP Tahoe at that time. And let's just have a look at the salient features of TCP Tahoe, that how it detect and react to the segment loss. So TCP Tahoe, it uses slow start, it uses congestion avoidance, it uses fast retransmit, and but what it does is that it always set the congestion window to 1, whether the loss is detected by timeout or the loss is detected by triple duplicate ACK. So TCP Tahoe was the first flavor. It possesses a very conserved behavior. It was the first ever congestion control algorithm in internet, first ever congestion control flavor of TCP. So it possesses a very conserved behavior, and it does what? It Whether the loss is detected by timeout or the loss is detected by triple duplicate acknowledgement, it does what? It sets the window size to 1 MSS. So go just right down to the bottom, and it then grows the window exponentially. So like went into the slow start phase, and then after hitting the threshold, it grows the window linearly. Okay, so then after the threshold is being hit, then it converts from exponential increase to linear increase. Okay, and this is the pictorial representation. No, sorry, first the FSM. Okay, let's have a look at the FSM. Okay, so we have only two states. We have the slow start state, and we have the congestion avoidance state, and we have an event of acknowledgement in the slow start phase, and when we receive an acknowledgement, we increase the congestion window by 1 MSS. Now remember, in the slow start phase, we increase after every egg we increase the formula was C wind is equal to C wind plus 1. It's exactly the same like this, C wind plus equal to MSS means C wind is equal to C wind plus 1 MSS. So we increase the congestion window by one maximum segment size, meaning by one segment after every act. Event is act, this is the action. Okay, and this will result in an increase of doubling the C wind after every RTT. Okay, and we will keep doing that until what? Until what happens? Until the C wind, is greater, it becomes greater than equal to the threshold, SS threshold. Okay, so we hit the threshold. We hit the threshold. When we hit the threshold, we do nothing. We just left the slow start phase and we move to congestion avoidance phase. And now we are in this phase, and now at each act we are doing what? C wind is equal to C wind plus 1 over C wind. Okay, which is exactly same as writing this one. Okay, so you are all programmers, so C wind plus equal to 1 over C wind means C wind is equal to C wind plus 1 over C wind. Okay, so after every act we will do this, just like the animation. Okay, and this will result in an increase of 1 MSS every RTT. Okay, every RTT, and we will keep doing this. We will stay in the congestion avoidance state until one of these events happen. We have a timeout or we have a triple duplicate ACK. So we detect segment loss either by timeout or by triple duplicate ACK, but I mean, we don't care. We just detect segment loss. We don't care whether it was detected via timeout or it was detected via triple duplicate ACK. We will do what? We will set the congestion window by 1 to 1, and we will set the slow start threshold value to C wind by 2. So whatever was the C wind value at this point when this loss was detected, this value divided by 2 is the new slow start threshold value, and we will leave the congestion avoidance state and we will move to the slow start state once again. Okay. Right, so only improvement that TCP Reno does, okay, only improvement that TCP Reno does is that, no, I mean, you can't have the same behavior when the loss is detected via timeout and when the loss is detected via triple duplicate ACK. Okay, so TCP Reno says that, okay, now I mean, you see, the world was very careful, very conserved, very muhtat because of the internet congestion collapse. So the Tahoe was something was a very careful congestion control algorithm, but first they have something up and running, then they say, okay, why not, let's try to do better. Okay, can we do better? So the betterment should be, I mean, why you are bringing your C wind to directly 1 when you detect the loss via triple duplicate acknowledgement? Because duplicate acknowledgements are indicating the fact that network is capable of delivering some segments. Okay, you see, when a sender receive a duplicate acknowledgement, it means what? It means yet another new segment was received correctly by the receiver. Okay, that's why I'm receiving a duplicate acknowledgement. Another received, that means another correct segment was received, I mean, whichever it was, there is a gap, there is definitely a loss, okay? There is definitely a loss. I don't know how many segments are being lost, but I do know that the oldest one was definitely lost. Let me explain. Let me explain. So let's assume that our window size is 16, n is equal to 16, and you see sender send all packets one by one. So packet 1, packet 2, packet 3, let's assume it is lost, packet 4 and 5 and 6 and up to so on, and packet 16. Okay, so n is equal to 16 is our window size. Okay, so packet 1, 2, 3, 4 and up to so on 16, right? And then we received acknowledgement, after receiving of packet 1, it sent ACK of 2, right? And then ACK of 3, and then you see 3 is lost, so after receiving 4, again ACK of 3, and after receiving packet 5, again ACK of 3, and packet 6, again ACK of 3, and up to so on. Okay, maybe not only 3, but you see also 4 was lost, right? Maybe the loss happened in the form of a burst, something like that. Okay, 3 and 4 both are lost. Okay, and but I mean, then again, when the packet 5 was received correctly, in response of 5, the ACK, which ACK would have been sent in response of 5? Anyone? In response of 5,
3,
when
sir.
5, again ACK of 3, right? So ACK of 1, ACK of 2, A2, you see A3, this is the original A3, and then first duplicate A3, second duplicate A3, and then 7 will be received, third duplicate A3. Now the thing is that there is a difference between these two scenarios. This is one scenario, okay? This is one scenario, and this is second scenario. TCP Reno says that TCP Tahoe uses a very conservative approach. If the loss is detected by timeout or triple duplicate ACK, it just goes down to C is equal to 1. No, this is not right. What I will do is that triple duplicate acknowledgements means that network is capable. You see, if I'm receiving A3, that means another segment received, another A3, another segment received, another A3, another segment. So network is capable of delivering segments. It's not that bad situation. Timeout means what? If the loss is detected by timeout, not by duplicate acknowledgements, that basically means what? I send something, I'm receiving nothing. No new acknowledgement, no duplicate acknowledgement, my timer expired, and my loss is detected not by this scenario but by timeout. It's a worst state of the network. Now in this scenario, I will do exactly same as Tahoe. I will do exactly as Tahoe is doing. Okay, same as Tahoe. But I will make a clear distinction if my loss is detected via triple duplicate ACK. In this case, I will not follow Tahoe because that approach is quite conserved. I will do what? I will cut the window size into half and then grow linearly. Linear growth means congestion avoidance, right? So I will not enter into slow start. Tahoe was doing what? Whether timeout, whether triple duplicate ACK, C1 is equal to half, and then I move to slow start. Okay, so I start from the bottom, from the beginning, from the, so this was the behavior of Tahoe, right? I don't care whether it is timeout or triple duplicate ACK. I will just, so for instance, this is triple duplicate ACK, right? Then even in this case, it will go down. C1 is equal to 1 and then slow start again. And then after hitting the threshold, move to linear. Okay, but Reno is saying, no, I won't do like that. I will do what? Cut the C1 into half and then grow linearly. This is what we called fast recovery. That's it. And now move back to the definition. Okay, when fast retransmit detects 3 duplicate acknowledgement, start the recovery process from congestion avoidance region. Okay, so cut your window size into half and start the recovery process from congestion avoidance region. Don't take your window size to 1, right down to the bottom, and go to the slow start phase again, but rather do this. Okay, so this is what Reno does, only the A step, not the second part. We'll come to the second part when we will discuss new Reno, but Reno does only the A step. Okay, let's have a look at the difference between the working of Tahoe and Reno. First, we'll come back to new Reno later. Okay, let's have a difference between the working of Tahoe and Reno. So this is Tahoe, slow start, congestion avoidance, fast retransmit, no recovery. Okay. This is the slide being shown over here, the pictorial representation, the graph. So time is on x-axis, on y-axis is the window size, and this is the green areas are depicting the slow start phase, the blue areas are depicting the congestion avoidance phase, and obviously the red part is depicting the MD part, okay, the multiplicative decrease. And anyone can tell me can we tell the difference between, you know, so I mean, let me ask, and I don't want answers from the, you know, regular participants, and I'm really thankful to all of them, but just someone new should, can anyone tell me what happens over here, what is happening over here?
सर टाइम आउट हुआ है
सर टाइम आउट
और वो
Okay, so segment loss
और
happened.
सीविंग
Okay,
हाँ
segment
जी और
loss happened
सीविंग
here.
1 पे चला
Okay, and C1
जी
goes to 1. Can you differentiate between whether loss is happened here and happened here and happened here, because this is also MD, right? Can you differentiate whether loss happened because of timeout or because of triple duplicate ACK? Can you differentiate?
यस सर, ये थर्ड में जो है वो ट्रिपल डुप्लीकेट एक्ट जो है उसकी वजह से हुआ है, और जो फर्स्ट और सेकंड है उसमें सेगमेंट लॉस की वजह से हुआ है.
This one, Abdul Basit, this one
Yes,
is
sir.
what?
ट्रिपल डुप्लीकेट एक्ट.
All agree, Ji? Thank you, Abdul Basit, for the answer. Thank you for participating. All agree, Ji? This one is triple duplicate ACK, and these two are, so definitely this is loss. You know, one, let's say 0.1, 0.2, and 0.3. All these three are losses, because loss is detected. That's why MD part is executed. Okay, we just go down to C1 is equal to 1, C1 is equal to 1, C1 is equal to 1, and then slow start again, slow start again, slow start again. Definitely loss is detected. But do you agree that this loss is detected at 3? It is detected via triple duplicate ACK. At 1 and 2, it is detected via segment loss.
यस सर
नो सर
No?
नहीं
Ali
सर
says no. Anyone else? Ali, just hold your thought. Anyone else?
सर वो ट्रिपल डुप्लीकेट एक और टाइम आउट में टाहो का बिहेवियर का डिफरेंस है ही नहीं कोई, तो हाउ
नहीं
कैन वी
है?
टेल
ओके, सो बिहेवियर बिल्कुल डिफरेंट नहीं है. देखें, सब में तीनों 1 2 3 ऑल 3 ओकेजन हम नीचे जा रहे हैं, और फिर स्लो स्टार्ट सी विंड 1, और फिर स्लो स्टार्ट सी विंड 1, फिर स्लो स्टार्ट. बिल्कुल ठीक कहा फाद अंसारी, आई थिंक इट वाज फाद अंसारी, बिल्कुल ठीक कहा. एनीवन एल्स? मैं जानना ही चाह रहा हूँ कि कैन यू टेल वेदर 1 2 और 3 वाज लॉस डिटेक्टेड वाया टाइम आउट और ट्रिपल डुप्लीकेट ACK? अब्दुल बासित कहते हैं
सर
कि
ये
दिस
जो
इज,
3 वाला है
नो
ना
सर.
ये टाइम आउट है 3
व्हिच वन
वाला
इज टाइम आउट? ओके.
क्योंकि वो 3 वाला
Yeah, so Abdul
सर
Basit,
क्योंकि वो वेट
thank you
कर
for
रहा
your answer and participation. Rukhsar, you are exactly right. It's vice versa. 1 and 2 is triple duplicate ACK, and 3 is timeout, and it can be observed and detected. This is, you know, we are waiting for a significant amount of time. We took time to detect segment loss. Time is on x-axis. We took some time to detect segment loss. Here, there is no time being shown. This means that we received 3 duplicate ACK, and we assume that definitely, based on the triple dup rule, segment must have been lost. We you know, fast retransmit, and then without doing fast recovery, we move to C1 is equal to 1, and then slow start. So this loss is detected via triple duplicate ACK. This is also 1 and 2, both losses are detected via triple duplicate ACK. On the other hand, this is detected via timeout. I'm running out of time. On the other hand, you can see the difference between Reno. Reno, when it will receive triple duplicate ACK, it will not go down to the bottom. So like this, you see, C1 is cut into half, and then linear increase, C1 is cut into half, and then linear increase. Okay. We just have TCP new Reno left. I leave this as an exercise. This slide over here, there is a difference. This is loss detected via triple duplicate ACK. This is what Tahoe does. This is what Reno does. And I want you guys to fill up this table. Okay. So understand what this table means and try to fill it up. Okay. Okay, so all we are left are with two slides. We will discuss what TCP new Reno is, and then we will discuss what the this FSM of the summary of TCP congestion control, and our chapter will be finished. And just last final announcement: we will finish the chapter on Tuesday, but the slides will be uploaded, and there will be a quiz from TCP congestion control on Wednesday. Okay. So there will be a quiz from TCP congestion control just from the lectures that we covered, starting from bandwidth allocation and congestion control. So just 2-3 lectures. Okay. So we'll have a quiz on Wednesday, but on Tuesday in the first 15 minutes we will discuss TCP new Reno and its finite state machine diagram, which is shown over here. Okay. Any question, Ji, from anyone? The
सर
class
किस
is
किस्म
over.
का
You
क्विज
can.
होगा?
It will not be. It will not